All right. Well, thanks for coming today. Nice to meet you. And so hopefully we can use this as a bit of a chance to like get a sense of what you're up to, and if there's ways that we can jump in and help, and maybe give you also a better sense of like what SimPEG is, and go from there. So normally we start the meeting with kind of like quick reports, but maybe we could even just do like quick introductions today if people are game to do that. So I can start. I'm Lindsay. I finished my PhD with Doug just a few months ago, and now am a postdoc here at UC Berkeley. I work with the Jupyter team. So I don't know if you've seen like Jupyter notebooks or the Jupyter ecosystem. But now I'm working on Jupyter in the geosciences, and so a lot of that is connected to SimPEG. So maybe hand it over to UBC folks.
Sure, go around. I'm Dom, we already met. I'm finishing PhD now, and I'm mostly focusing on potential fields. So all the parts of gravity magnetics of the package, I was heavily involved with them. And yeah, that's it.
I'm Mike. I'm also trying to finish up my PhD, mostly like DC resistivity type methods, but also a little bit of EM type stuff.
Good. So I'm Ali. I'm a hydrologist or hydrogeologist working on stream flow processes and how catchments respond to precipitation. So in terms of the model calibration work that you are doing on like air system processes, so typically in hydrology, people use stream flow to calibrate their model. So now modern hydrology look for more functional based calibration, which focus on multi-objective calibration with different components of the stream flow rather than only one component of the stream flow. So simultaneously we calibrate model with 6, 7 objective or objective functional responses. Let's say that. And that's why I think such like a platform such as SimPEG, it's if it would be flexible and easy to use, would be very useful for my research, because now we are looking for multi-objective calibration rather than only calibration with one objective function.
Can you explain what is?
Typically in hydrology, typically stream flow, we measure a stream flow in the stream, and we try to calibrate our physically based model, which is based on the physical processes of the earth and landscape, to calibrate the unknown parameter, to play with the model to tune our objective function, which is a stream flow. This is the typical application of calibration in hydrology and hydrogeology or groundwater modeling and so on and so forth. But recently, the focus is more on a multi-objective calibration because of the, I'm not sure if you may have a different term in your in your field. We call it eco-finality, which means that when you calibrate a model, you can get the good calibration for a wide range of different combination of parameters. So, but only one combination of these parameters is true. So now the question is, which of these combination can better represent the air system processes, because at the end of the day, we are going to use this model for climate change and land use change prediction. Right. So if the model, we have like a sentence in hydrology that we call it getting the right answer for the right reason. When we are using a stream flow and calibrate model with the stream flow, we don't get the right, we get the right answer, but for the wrong reason. You know, that's why this model is not that efficient for future prediction, for climate change prediction, for land use change prediction. But the modern approach in hydrology focuses on multi-objective calibration. So we get a stream flow, because the other problem of this, because of uncertainty in the measurements. So a stream flow includes a wide range of uncertainties, and you don't know which where the uncertainty came from. So in a modern hydrology, we're trying to find some signature of the catchment, and before we immediately use a stream flow hydrograph, we trying to find some objective out of that stream flow hydrograph, some signature that show the functional behavior of the catchment, and then we calibrate our model with those signature instead of immediately go ahead and calibrate the model with total stream flow. In this case, we can consider the processes at different depth of the landscape, because at different depth of landscape, we have totally different processes. At 1 meter, we have hydrological processes, which is totally different from the hydrologic processes or hydrogeologic process that occurs 20 meter deep or 50 meter deep. So because we have different components that contribute to stream flow, we are going to calibrate the model with these different components rather than calibrate the entire model with 200 parameters with just one objective function. So having said that, once we're going to do this calibration, it's not easy to do that with, I'm not sure if you're familiar with PEST. PEST is the calibration platform that I used in my master like a 10 year, 20, 15 years ago. It's like an old-fashioned calibration platform for hydrology and groundwater modeling. But nowadays, doing this sort of calibration with multi-objective responses is not easy with PEST. That's why I'm thinking such a platform, if they are user-friendly, if they are flexible, would be very useful for a modern view of hydrology, which will focus on multi-objective calibration.
I just got a quick question. So, nice to meet you, I'm Sagi.
Yeah,
Ali. So, Ali, so PEST is basically a gradient-based inversion, right? So, gradient-based calibration. So, it provides like a kind of easier way to compute that gradient function, correct?
Yeah.
So, is that still works well, or like do you still want to use the gradient-based approach, or do you want to kind of move around for other types of? What's your motivation? You know what I mean? So SimPEG is built up for a gradient-based inversion.
Yeah, it's a very good question. I think most calibration approach in hydrology focuses on that gradient-based, traditional gradient-based thinking and approach. So I'm not optimization person. I'm actually my focus is more on the science part. Mm-hmm. And my background is all engineering, but I've been away from engineering departments for 3 years, 4 years. And my focus was mostly on the physics part and science part rather than the numerical part. Mm-hmm. So as far as I can remember, the status quo of optimization in hydrology was based on gradient-based model. I don't know if it's good or bad. What's the disadvantages? For my master thesis, it worked very well for me, the PEST. But nowadays, I'm not going to use PEST or this sort of approach, only because they are not flexible enough to consider a different type, simultaneously consider a wide range of signatures for calibration.
Yeah. Good for us.
Yeah. But actually, I would like to know what's the basis of the current approach, specifically in SimPEG. So what's that objective function that you use? Is it a gradient based? Is it something alternative? I would like to know more about that. Yeah.
I just want to clarify one thing. You mentioned multi-objective function. Okay.
Yeah.
And then, does that mean are you using kind of different physics? Is that?
Yes, exactly. So actually, let me explain it in more detail if we have time. So imagine we have so water in the stream comes from different compartments of the landscape. One compartment is the very overland flow that you see the water moves over the land, which we don't see that in BC. It's more the process in Prairie, in Saskatoon, in Manitoba. So in some regions, the dominant runoff process is that overland flow. In some regions, which is the mainly part where we can see the process in BC specifically, the most water, the dominant water in the stream comes from the shallow subsurface flow. Within the soil, in a first 1 meter, 2 meter of the soil, because it's forested soil are very permeable, water moves down quickly, and then is either evaporate or transpired by the trees, or get into the stream through the shallow systems. And in some region of the world, water go even down, go to the groundwater storage of the system, go to the rock, and then we see water discharge into the river, down valley rivers, large rivers, through the rock. So in hydrology, we have these three different processes that contribute to a stream flow. And it might be interesting for you that, so we can call them separate compartments, because water moves at different and you know that these three different compartments have totally different processes, parameters, and so traditional hydrology only calibrate the model with one stream flow that don't care about this compartmentalization, and try to calibrate 200 parameters of all these three compartments together. But nowadays, we know that they are coming from different compartments. They have totally different behavior. So we have to calibrate processes that occur within each three compartment differently and separately. Not separately, because at the end of the day, they're going to join together. There is a what's called in mathematics, there is some constraint that link all these three equations together, all these three compartments together. But initially, we have to consider them separately and then link them together. And the linkage would be water that we measure in the stream or river.
I see. Okay.
Sounds like a combo.
Cool. Let's maybe finish off with introductions, and then we can.
Okay.
Yeah, so my name is Devin. I was a graduate student here, and now I've been working for the UBC group for the past 2.5 years. I've got some software projects unrelated to SimPEG that I work on, but what mostly I've been doing with SimPEG has been documentation, tutorials. We have all sorts of tools that we've been developing, and now we're realizing it's time to try and entice new users, get people up and running a lot faster. So I'm putting some energy towards that.
Good.
I'm Kevin. Nice to meet you. I'm a research assistant. Here at GIF, I've been for about 4 months so far. I focus on a project. Basically, it's about groundwater geophysics in Myanmar, or Burma, as it was formerly called, for humanitarian purposes. And basically, the idea is that we're using SimPEG or aspects of it for the DC resistivity side to do surveys there to image the optimal places to drill wells.
Good. So you said you're part of Jeff Force, right? Jeff's group, or you said?
I'm part of the UBC GIF group. So
What's UBC Jeff?
So, well, yeah, basically it's the big group that we're part of at UBC. So everyone that's working with Doug Oldenburg. So SimPEG is something that we've been working, and then we also have software and version codes and things for our sponsors.
Good.
It stands for Geophysical Inversion Facility.
Okay.
Yeah. So all these electromagnetic conversion codes, kind of the thing that we've sort of based SimPEG or the numerical approaches for SimPEG. So we had these Fortran codes. Now we're open sourcing everything.
Yeah, I'm Bahir. I'm involved in gravity and magnetic modeling. Actually, in a sabbatical period on Institute of Physics at University. I said a few months that I'm using SimPEG and Python for modeling the geothermal resource. The data from Mahana TV. Two set up integrity and one set that I'm trying to model with my university into this new facilities in a part of give all of them.
Thank you.
Back to you, is it? Oh, Sagi, yeah. Introduction, Sagi.
Hi, I'm Saki. I did my PhD back in UBC. Now I'm at Stanford, actually working on groundwater problem, but in a geophysics site. So I'm trying to help solve like 100 questions using some geophysics. That's what I'm doing.
Oh, recharge the question you said?
No. I'm help solving hydrogeological questions.
Okay. Yeah. So what type of questions?
Well, let's say like let's say subsidence is a problem, then we want to like use geophysics to figure out what is the distribution of clay fraction, for instance. And then if you care about the connectivity of the aquifer, like what kind of geophysical methodology you can use to say what is the probability of like the aquifer is connected or not, or something like that. Like that's
yeah, connectivity is my buzzword. Like, actually, it's my field of expertise. So what exactly do you do? What's the scale of your work? Is it like a small plot scale? Is it catchment? Is it watershed? So at which scale, at which spatial scale you're looking for connectivity?
I think I guess it's a catchment scale.
Okay.
What we're doing. So like yeah, the survey that we're doing is about like like a 10-kilometer scale, like a 10 kilometer by 10 kilometer area.
And who are you working with?
I'm working with Rosemary Knight.
Okay, I know. Yeah.
Nice to meet you.
Yeah, nice to meet you.
Sort of connected problem.
Yeah, it's very interesting that you guys are all working on different aspects of the different disciplines. Very interesting.
Also math.
Yeah.
Yeah, it's pretty cool. It's a diverse group, and that like helps, I think, motivate a lot of the way we've tried to develop SimPEG and are still continuing to. So to give you perhaps a bit of an overview, Dom, I might just mute you and then, or if you don't mind muting and unmuting, I'm just getting a little bit of feedback. Thanks. So feel free to unmute or wave at Dom if you want to jump in. Yeah, so SimPEG stands for Simulation and Parameter Estimation in Geophysics. And so it's set up to be like a very modular code base. So what we've tried to do is basically set up a package called discretize. And so what it does is all of the meshing, and it gives you all of the differential operators so that if you want to basically write down a PDE and solve it, you can do that. So we have like, you design your mesh and then you write out what PDE system you want to solve. And then discretize lets you translate that to solve your PDEs. And then SimPEGs, can you unmute?
Sorry to interrupt you. So PDE and solve, what's the method that you use to solve the PDE? Is it finite element, finite difference, or?
Finite volume.
Finite volume.
Yeah.
Okay. And so as far as I understood, the platform is flexible to any type of PDE, any type of equation. Is it? Can you a little bit explain it? What type of equation?
Yeah, sure. And Dom, actually now it seems to be better, so maybe we're okay. We'll give it a try. I'll let you know if it starts bugging me again. So right now we have basically easy interfaces to potential fields, DC resistivity, electromagnetics, and Richards equations.
What was the last equation?
Richards.
Richards, okay.
Yeah. So those are basically set up so that you can use them at a high level and just say, like, solve Richards equations, here's my physical parameters. But if you actually want to write down a different set of partial differential equations, if we want to do Darcy flow, for example, you need to assemble that. But that's something that we can help with and is easy to do. So all of the, like, it depends on like what level you want to interact with. So if you want to be running a whole bunch of Darcy simulations or Darcy inversions, then we want to actually plug that into SimPEG so that it's something that you can reuse very easily. If you just want to explore sort of different sets of equations, you can still do that at a lower level. You just have to write out what they should be in code. Dom, can you unmute again? Sorry.
Yeah, and any attempt have been so far met because I can see you are from different disciplines, geophysics, solving Richards equations. So any attempt have been made in your group to couple these different disciplines together? I mean, calibrating and developing a coupled model which considered both geophysics equation and Richards equation.
Yeah, so there's not been tons of work like really diving into coupling these things, but what we have done is we've laid all of the groundwork to make that possible. So right now, all of the machinery is in place to basically assemble whatever objective function you want, and that can include Richard's equation and DC resistivity as long as we have a way to couple them and to solve that. So all of the machinery is there, and then Thibaut, I guess, is not around, but Thibaut's work has looked a lot at actually combining multiple data sets to solve one inverse problem, but coupling them through physical property distributions.
Mm-hmm. Good. And a very last question. So forget about calibration. Like the similar platform that I've seen also consider sensitivity analysis. So imagine we don't have data in some places, or either in geophysics or in hydrology. So any chance that the platform can also do like a more, for example, if I'm not mistaken, it was Moore's sensitivity analysis, one of the simplest sensitivity analysis I've seen. So any chance that the platform can do that too?
So I'm not familiar with the specific sensitivity example that you stated here, but we do construct, so SimPEG is set up to do gradient-based inversions. And so with that, we have access to all of the gradients. So we can, for a given model, compute what the sensitivity is. So we have all the machinery to compute sensitivities. And then what you choose to do with that is up to you at that point.
Mm-hmm.
Good answers.
Good.
Cool. Yeah, so when you were talking about the 3 different like modes of flow that you want to consider, do you actually have running simulations for those already, or is that something you'd be interested in writing, or do you already have a code that you want to try and plug into SimPEG? How would you envision solving the problem?
Yeah, that's a very good question. So there are 2 different approaches in our field. One of them is kind of applying Richard's equation that it's been already adopted in SimPEG, and so we can consider because it's a physically based approach. You can consider the properties of the soil. It's going to be the first compartment. You can consider the property of the rock is the deepest compartment, and also you can consider the some parameters and properties at the top, which controls the overland flow. So this is from the physically based perspective. Just imagine you are solving Richard's equation, nothing else. So it's not something beyond solving simply Richard's equation. But the second approach, and in the first part, I'm not sure how fast is SimPEG. So imagine a catchment. You're going to solve Richard's equation for a 100 kilometer square catchment. How long does it take for 1 year simulation?
That's not something that we've pushed on too hard right now. There's still some work that needs to be done in terms of efficiency. So if you have need to start going to that scale, then we can chat about like how to do that. We do have some pieces plugged in, like octree meshes and things like that, which can help with efficiency. But right now, running like 100 kilometer by 100 kilometer at reasonably high resolution would be really pushing it.
Yeah, so that's why people in hydrology actually resorted to some simpler approach rather than solving Richard's equation with all its nonlinearity. So your computational time is because of the nonlinearity of the equation. So if you have a very simple equation, you can easily solve it for a larger system, for sensitivity analysis, for calibration. And so the other approach in hydrology, rather than physically based model, is the lump model. So you consider, imagine what I said, you consider 3 different compartments. Imagine we call them buckets, we call them bucket models. You consider 3 different buckets. One bucket at the top represents overland flow, the second one soil, and the third one the rock, bedrock. And then you start to calibrate some not physical parameters here. We don't care about the soil hydraulic conductivity of the and physical properties of the systems. Rather, we care about some, let's say, mathematical parameters that may not have any interaction or relation to the physics of the land, of the below the land at all. So these parameters can be the depth of the storage. So it's very mathematical parameters. It's not physical. Like a time that water takes to leave the storage. All these three different buckets. So, and that's why we end up with like hundreds of parameters which are not physically based at all. These are just mathematical models. And then you try to calibrate your system with these non-physical parameters. In this approach, it's very fast. So for like a simple platform, simple calibration platform, not even as a sophisticated as SimPEG, it may take like a 10 seconds to simulate a 10-year simulation of hydrologic model, because there is no nonlinearity here, just a couple of equations. And this is what I've seen that's been typically used for the type of approach that I'm thinking. 3 different compartments, you can independently consider 3 different pathways of the water, 3 different compartments of the water, and then link them together with hundreds of parameters. But you can get good answer because it's simple, and at the same time you are separating different processes. So how feasible is it in SimPEG? Imagine we are going to deal with some buckets and 100 parameters related to these buckets.
Pretty easy. One thing we often do also is to change the resolution in different parts of the model, right? So if you have something that is deep, then you can have a larger resolution, reduce the cost that way. Or a different parameterization overall, like a mathematical.
And the equation here is very simple. We have a storage of the bucket that we calibrate with the data, and the equation here is just some threshold-like equation. If the storage of the water in the bucket fills, or it just fits the storage, it moves to the stream. If not, it lives in the storage. So it's not Richard's equation. It's not very sophisticated and difficult and nonlinear equation to solve. So, and I don't think it's been solvable with finite element at all, because we just have one ordinary differential equation. We don't deal with PDE. So how feasible is that in SimPEG?
You'll have to write it. But
okay. And it's Python, right?
It's all Python.
Good. So it's it's very easy, and
as long as you're willing to some time.
Yeah. So in that case, it sounds like you have like you don't even actually need the meshing side of things really, if you just have an ODE with lots of parameters, right? Like in this case, it's much more sort of the inversion machinery that might be of use if that's the approach that you want to take. Correct me if I'm wrong, but that's sort of my interpretation of that.
Or a combination of 2. One, right? You're gonna have a part that's going to be more PDE, and a part that's going to be just a simple parameterization.
Good.
Is that what you're saying? Right?
Yeah, exactly. So there are 2
how they interact with each other.
Exactly. So like a master student who knows Python very well can easily develop that, right? In terms of the flexibility of your platform.
Definitely.
Yeah, I think, was Thibault going to run a tutorial or DOM? I know that there was talk of that on the Slack channel. Was that on the radar, or did that already pass?
A tutorial, like a general, like a Python tutorial?
No, a SimPEG, or SimPEG related. I know Sarah had requested.
Yeah, so like last Thursday, we did one.
It was a Git, right? It was all about.
Yeah, it's mostly about Git.
I think the focus, was more Git, and what is a pull request, that kind of stuff.
It's kind of on demand whenever there's need, right?
Yeah.
Yeah.
I don't think there are plans for another one, but if somebody has a suggestion, then I suppose.
I'm wondering if the groundwater project that Kevin is leading, if there might be like potential reason to have like a small working group or something like that, where just like getting up and running and playing with SimPEG might be a helpful thing to have on their radar. And there's a question of timescales and all of that. If this is worth starting right now, or if you want to like explore or have students explore a bit first, and they're always welcome to join meetings as well. Yeah, so that's something that we can think about. I don't know if you have immediate thoughts on that, Ali, or if that's just like something we want to follow up on.
Actually, for now, I'm thinking. Yeah, actually, I'm looking for students to start working on that. And one follow-up question. So how? Because there is also a hydrologic model that's like a developing model a couple of years ago, and it's actually based on Fortran. But this model has no optimization or calibration tool yet. So how easy is that? How easy is to like couple this sort of approach together? Like a open source hydrologic model that developing Fortran to link it with SimPEG for optimization processes, for calibration processes, because that platform already consider all what I said, both physically based approach and bucket based approach. So and it depends on the user to select which one he or she wants based on the data, based on the scale of the system. So, but there is no calibration or optimization platform linked to that. How easy is to link these two together?
So you can definitely plug it in right now. There's a question though of how expensive the simulations are, is because to do gradient-based optimization, we need an estimate of derivatives. And so in that case, one thing that you can do is like we can do finite difference derivatives, but that then means we need to be able to basically like independently take a step over each parameter. And so there's a lot of simulations that need to be run. But that, sorry, he was just pinging me. I'll come back to his question in a second. So yeah, so it depends on if you have machinery to compute derivatives or sensitivities or not. And if not, how expensive the simulations are.
Okay, yeah.
So do you have sensitivity?
At this time, no, because it's not my model, but I can check the manual and yeah, I'll let you know. So you mean the optimization at the stream. So I'm thinking in terms of the gradient-based optimization. So you mean if that platform can on its own calculate these derivative and sensitivities or not? Your question is that, right?
Yeah. Yeah.
I think it can. It can, because, and also it's so fast because it's the bucket. When it comes to the bucket-based module of that, it's so fast, and that's why we can run it for millions of times in a minute. You know, so calculating the sensitivities and gradients is not that difficult for that one, and so fast.
Excellent.
So, I now get it. So you mean the input of SimPEG? Sorry, I've been away from the optimization for like 10 years, but I can't remember the process now. So you mean the input of the SimPEG can be as easy as the gradients, right? Gradients of the state variables. And once you have it, you can get the SimPEG run the optimization. I get it now. Yeah, yeah.
As long as you can call your program from Python and say, give me derivatives, and then it gives you better derivatives, then the rest is...
Okay, and is it easy to link Fortran to Python?
There's, yeah, of course, well, I can't remember what's the package, but...
FPy.
Yeah.
Yeah,
FPy. Yeah, it's just
Fortran to Python. Yeah, so that makes it pretty straightforward to do.
And doesn't hurt the speed of the process, right?
That's not something I've hit on or like really jumped into enough to be able to answer for you. But I think based on the stuff where like Soggy has worked on the EM1D code, there are pieces of that are written in Fortran, and calling that from Python is still faster than having it written in pure Python. So there's, even if there is a little bit of overhead, you still are benefiting from the Fortran speedups.
For now, I'm thinking, the coupling of these two would be the most time efficient approach, because it's just ready, you know, it's both parts are ready and you're just gonna link them. And even a master student who is who might be expert in the other fields rather than optimization can do that easily, as long as he or she knows Python. So I think this is what I'm thinking for now. So I'm thinking to hire a student, master or PhD, for this January or May, next May. So this coming January or next May. So then he or she gonna start working on that.
Excellent. Well,
Yeah.
and I think that that timing is perfect too. We're working on doing a little bit of cleanup on the API so that it's easier to interface between like SimPEG and other forward simulation codes.
Good.
And so like that's going to take us a couple of months, but I mean, if you're not hiring a student until a couple of months, then that timing's perfect.
That's great. And just a quick question: what should be the qualification of that master or PhD students to work with Python, or in general work with your platform easily? Because I'm not gonna hire a student who is gonna spend like the first 6 months just learning the basics, you know. So what would be the qualification of that student, in your opinion?
I mean, I guess like some programming experience is definitely helpful. I mean, whether or not it's Python, like if they have experience in Python, that's great. Most of us, I think, well, at least speaking from my experience, I hadn't used Python until I started my degree, like my PhD. I was coming from MATLAB. So I think like it's much more, as long as they have some sort of programming experience, I think that's important.
Good.
And then it's a question of like how deep you think that they should go on the numerics side of things. And the optimization side of things. Do you view them more as a hydrologist and somebody who's just really using these techniques and doesn't necessarily need to go so deep that they need to be able to like program up different optimization techniques? Or should they have some optimization training?
Yeah.
And there's a lot of good courses in the CS department. The CS department at UBC is like really solid on the PDE and optimization side of things. So even if they like, as long as they have some numerical inclinations, there's definitely like room to grow in that space.
I get good. Yeah.
And Sagi just asked a question. So he was asking, so when you're calibrating these models, are you calibrating for distributed parameters, or are they basically like parameters on each bucket?
Yeah, that's a great question. For now, it's just one parameter for each, not one parameter, but it's not distributed. It's just it's the lumped, let's say lumped parameter for each part of the model. So, but how about distributed in the future? So how easy is that to calibrate the distribution for a parameter? Because it's also one thing I'm thinking like for like the next 4 years, next 5 years to go to that.
So SimPEG is actually more set up to calibrate distributed parameters. Because we have like the regularization in place to basically spatially regularize things, and Dom's done a lot of work in that space of figuring out like should bodies be compact, or are they smooth, or and how do we impose that mathematically? So a lot of that machinery is actually there, and now we can like optimize for sort of just like discrete parameters that don't necessarily have spatial correlation. But the question I wanted to follow up with here is, like, do you have a sense of how those things should be regularized? Or are there reference values for them, or are they basically just like free numbers that we can fit anything to?
Actually, we can have a range for each parameter. So, and but it's not that distributed per se. So imagine hydraulic conductivity may change 10. The median of that might be 10 to -5, and the range might be 10 to -6 to 10 to -4. So this is the range of parameter that we can have, and then we let the optimization tool to select the best fit for the observations. But in terms of the distribution, I'm thinking because you know that so this is mostly applicable for bucket-based approach. But when it comes to the physically based approach, and we're gonna do the optimization for the entire catchment, so we would better to consider a distribution of the distribution for hydraulic conductivity, which actually embraces a large range. It's not that small range. So yeah.
Cool. Yeah. I mean, so there's examples. I can send you to the paper that we have on Richard's equation, because that can give you just perhaps a bit of an idea of like the I guess like higher or like the more physics-based end that you can explore with SimPEG. And then yeah, if you have like a sketch of the codes that you want to interface with, that's something that we can work with the student whenever they get onboarded, basically how to plug all those things in.
Yeah, sure.
Super cool. Cool. Well, do you have any other questions while we're on this topic? Otherwise, we can maybe do a quick like round table and see if there's any other items people want to chat about today.
No, I don't have a question.
All right. Yeah, so any other things people want to bring up, go over? John, do you want to start? And we can just go around the table. If you don't have anything, that's fine.
Yeah, I have nothing to report. I mean, it's the same list. I just, I'm on other stuff right now, so nothing new for me.
Fair enough.
Yeah, I still have a couple open PRs, so I've made the changes to the discretized pull request for tutorials. Just doing the finishing touches on the advection diffusion. So corresponding with Soggy on that. Hopefully figure that out by today. The SimPEG one for meshes and mapping tutorials. So I think Sarah took a look at that as well and was pretty happy.
Excellent.
But there is some, was it like, Sphinx, intersphinx something? There's something that seems to be breaking the docs, so that PR is failing, and I haven't been able to locate the source of that.
I can take a look. I think it's because we have moved where the discretized docs live.
Yes.
They don't live on the docs anymore. Yeah. Ping me again this afternoon if you don't hear from me on that. But I also want to say, Devin, like, congrats on making some beautiful tutorials. The discretized ones are like really, really well done.
Okay, that's good. Yeah. Yeah.
Are they going to be updated soon?
Yeah. We want to try and merge them in like today or tomorrow. You can get it if you wanted to, but yeah, it's a really.
I can wait. I need them right now. But
I know a lot of you people have been asking them. So, but yeah, so those are basically getting done. But I gotta, deal with a few comments first, and then we can bring it in, and any of the sort of remaining stuff we can work on that in a new PR.
Excellent. Thanks, Devin.
Yep.
I don't have that much new to report, but Lindsay, you sent me that code in your EM notebooks repository, and you had something called, I think it was DC inversion to the example, and I've been playing around with that and changing up the mesh size and that kind of stuff, and seeing what happens as recommended. So.
Super cool. And I added you to the SimPEG research organization on GitHub. So if you want to create any new repositories and just like store code there, you certainly can.
Okay. That mind.
Cool. The quick update is there anybody else who had things? I can only see part of you, so I can't see and that's okay. I had a good chat with John yesterday from DIAS. He's really interested in jumping into the MT code. Sorry, Ali, MT is magnetotellurics, if you're not familiar with that. And so he has started a pull request looking at a few different receiver types. So the example that they're looking at is they've got like a handful of electrode locations and then a whole bunch of mag locations. And then so wanting to basically compute transfer functions between all these different things. And so I think he was successful in getting something up and running there. And so we'll start diving in and taking a look at his pull request and try and get him deeper into the MT development. So if anybody else is interested in like keeping tabs on that, feel free to jump in on the pull request and just, let him know you're interested and want to be kept in the loop. And then the other one is I started a pull request on it's a work in progress, so it's still like very much under construction, the simulation refactor. So Ali, this is actually relevant or will be relevant for plugging in other codes. There were some things, just some assumptions that we made early on in the way that simulations are set up in SimPEG that was like a little rigid and didn't necessarily let us plug in other codes very easily. So I've been working on like basically trying to tease out some of those assumptions. So it's easier to basically write like a single wrapper that wrapper class that knows how to compute data and to compute sensitivities. And if you have that, then we should be able to plug in other codes to like work with SimPEG. And so what I'm going to try and do with that pull request, because it does touch a lot of code, which is kind of challenging because like, you know, you turn something at the bottom and it impacts everything above it. So I'm trying to go through the modules with like a very light touch and update things. And so what I'll try and do is basically like ping people who I know who have done work in giving components and just like ask you to test it out, make sure that this thing is making sense. And then perhaps like we can chat about perhaps like a few more changes that might be nice to make, but aren't like critical for the next step. So you can sort of expect me to like ping you in lines of code on that pull request. So yeah.
That's great. I have one question for you, Lindsay, more like an advice. So Nick messaged me yesterday and asked a very good question. So we're doing sensitivity weighting and kind of taking over the cell weights of the regularization.
Mm-hmm.
So then we don't have two levels, right? If the user wants to set their own weights, we're kind of overriding it.
Mm-hmm.
Do you think it should be better if we have either two levels in the reg, or we just do it in the directive, we override temporarily in the directive?
Let's maybe sketch this out in the issue, but my gut instinct is to let the user set stuff on the regularization and then take care of the sensitivity weighting entirely through a directive.
Yeah.
Because it's updating at every step anyway, so it's kind of nice to have the regularization just like be its own thing, and then the sensitivity weighting like ticking at every iteration, and then just basically updating, like multiplying the diagonal inside the W matrix. Does that make sense?
Yeah. Okay, we'll have to think about it because like somehow the directive will need to hold and store the weights and then reapply it at the end, because we don't want the regularization to change, and this is what it's used in the when it's like the derivatives of it. But yeah, okay, that's good. That's what I thought too. That's good.
Yeah. Feel free to sketch it out, or if you have like a pull request started or something like that, we can hash it out. But I think that's probably the cleanest way to do it.
That's fine. Yeah. Good. Gotcha.
Cool. So the only other item I see is that Sarah looks like she's interested in presenting next week on her DC resistivity work on the irrigated potato field. So yeah, so that will be the main topic for next week.
Perfect.
Excellent. Well, thanks everyone. Thanks for joining, Ali. It's great to meet you.
Yeah, it's great to meet you too. So please let me know for like a next like a future workshops, tutorial, and everything that you think might be important for the type of research that I'm working on. Also, speaking of advection dispersion, so is this just for flow or for
advection? It's just a really simple toy example to get people to learn, how to start from scratch. You've got some kind of time-dependent PDE. You're going to have some boundary conditions. You're going to apply finite volume discretization, and then you're going to solve it numerically entirely with discretize.
Okay. So and you should have some like a flux flux result before that to link it, right?
No flux leaving the system. It's just a very simple toy synthetic example. It's to try and get people to learn how to use the tools.
Okay, so but at the end of the day, it's going to be very useful for like a transport process, specifically hydrologic transport, water transport, contaminant transport. this should be linked with Richard's equation. You know?
I think you're taking it to like a level of practical
Yes.
next level research.
Yeah.
I'm thinking of
Just
we
very
have
simple.
this software package and people don't know what the syntax is. How do I go and call the divergence operator? How do I put in boundary conditions? How do I make a mesh? You know, we want you to be able to learn all the tools first. And then once you do that, you'll be smart enough to construct a problem-specific discretization.
So by advection distribution, you mean your focus is mainly on the type of equation, not on the physics that it can bring.
Yeah, exactly.
Science
It's just we have a convection diffusion equation. We put in a couple parameters. We keep it pretty simple.
It's great start because
Yeah.
probably in the next couple of years we can link it to Richard's equation. It will be awesome because none of the hydrologic model can do that easily. You know, it's very difficult.
Yeah, and one of the things I want to accomplish with this tutorial is we have a section on numerically evaluating inner products with the finite volume. And if you have this library on how to numerically approximate these inner products, you have the little puzzle pieces for any PDE that contains these.
Yeah.
So that you would be able to go in and say, oh man, I got this PDE, it's got this term and this term and this term. How do I take the inner product with that? Oh, go to that section, pick them out, and then you're like, oh cool, I have everything. That's kind of the idea.
Yeah, that's a great start. Yeah. Good. Yeah, that's great. Thank you for having me.
Oh, very glad to have you. And we can add you to Slack. That is where most of the conversations, we just sort of like keep in touch day to day there. So you're welcome to join if you like.
Sure. Yeah. Great. Thank you.
Well there.
Yeah.
Thanks, everyone.
Good day, guys. Yeah, good to see you. Yeah. Bye.
Yeah.